Hello, students, and welcome to the video key for worksheet 4, which is part 2 of chapter 3 on acids and bases. Okay, so we're going to start off in this part 2 activity with inductive effects. Note that we are not going in order of ARIO. We did talk about the atom, which is A, but we're going to cover inductive effects, which is the I before resonance. So we're just covering them in a slightly different order, and it shouldn't, affect anything. Okay, so we are going to be talking about inductive effects, which is the presence of electron withdrawing atoms or groups that can help stabilize a base, making it a weaker base. And so it gives you some examples of what are some electron withdrawing groups. So starting off with just electron withdrawing atoms, let's look at these structures, and it asks us to draw the structure of the conjugate base of the following carboxylic acids. So we are just going to remove this proton and then add another lone pair and a negative charge in order to get to the conjugate base. So we have very similar structure, and you can go ahead and add in the lone pairs if you want. I always like to see them so I kind of keep track of all the electrons. So when we lose that proton, we'll get a third lone pair on that oxygen with a negative charge. So in this case, we have still CH2 with a hydrogen attached to it. And then in the case where we have the second structure, again, the carboxylic acid part, which is really this part, stays the same. And the difference is now we have an iodine at the carbon attached to the carbon bearing the carbonyl and oxygen with negative charge. We can just keep sort of going through this process of drawing out the conjugate base. A little bit time consuming, but we'll get there. All right, now we have all of 5 conjugate bases drawn. And it asks you what is structurally similar, right, between the conjugate bases and what is structurally different. So if I just sort of draw a generic structure here, I'm just going to show that, right, this entire part, and then let's go with X. Right? So we'll kind of circle. This entire part is structurally similar. Right, and the group attached to the carbon here, whether or not it's a halogen or a hydrogen, is what's structurally different. So then it asks you, based on the pKa values, rank the conjugate bases of the acids in the order of increasing basicity, with 1 being the strongest base. So you guys will remember, hopefully, from the last activity that the stronger the acid corresponds to the weaker conjugate base. So looking at these pKa values here, right, we see that this is the strongest acid. So don't forget that the lowest pKa value is the strongest acid. Okay, so if this is the strongest acid, then this would be predicted to be the weakest base. So we need to march our way up to the strongest base. Okay, so let's go with 5, 4, 3, 2, 1. Okay, so I'll just write my hopefully it's clear that I'm answering this question with these red number values. So, right, let's see what the next question is. Does having electron withdrawing groups weaken or strengthen the base? Right, so we said that this was the strongest base, and look how it does not have an electron withdrawing group. And as the group gets more electronegative, then we actually weaken the base because this is helping to stabilize part of this negative charge. The negative charge over here that's shared between the two oxygens through resonance, right? Some of that electron density gets pulled towards the fluorine, making that have less negative charge in this direction. And as a result of less negative charge, then it's more stable, right? So definitely say electron withdrawing groups weaken the base. Right, and then we can even put because it's more stable. Let's see the next question is looking at these oxy acids. And first it says to draw the structure of the conjugate base of the following oxy acids. You can see how it has this nice hydrogen drawn in. We just want to remove that to form the conjugate base. So we will basically just copy the rest of the structure. And again, if you want to, you can put in all the lone pairs, 2 lone pairs on each oxygen, 3 lone pairs on this oxygen, okay? Or you can leave them off with the knowledge that they are there and that you know that they're there. Okay, so we've drawn in the structure of all of the conjugate bases. And then if we look at the next page, I think it continues on with asking us to work on this. And it says to, based on the provided pKa values, rank the conjugate bases of the above oxy acids in the order of increasing basicity, with 1 being the strongest base. Okay, so again, right, we have lower or more negative pKa value is a stronger acid, right? So stronger acid corresponds to weaker base. So we would work our way up to strongest base, which would have the weakest corresponding acid. Okay, so you can see that having a knowledge of pKa values is definitely helpful in understanding base strength. But even without the pKa values, right, think about how you might have rationalized this base strength. So recall that bases are stronger when they don't have a bunch of electron withdrawing groups helping to stabilize the negative charge. So the presence of more electron withdrawing groups as we go from right to left will help stabilize that negative charge, making it a weaker base, right? And that makes sense. This is the weakest base, right? And this is the strongest base. So even without those pKa values, we probably could have figured that out based on our knowledge of the inductive effect. All right, so moving on to question number 8. It says, let me see if I can get this a little more. Yes. Tends to get out of focus just over time. Okay, use curved arrows to depict the following acid-base reaction and predict the product. In the empty box, predict the position of equilibrium of the reaction. It will lie to the left or the right as drawn. Okay, the first example has been completed as a reference. So let's see what's going on here in this first example. So they've noted that the atom with the negative charge is probably the base. So it's taking the proton from what's going to be our acid, and that lone pair gets left, or the set of electrons in this bond gets left as a lone pair on this oxygen atom. So then based on what we have here, with the transfer of the proton and the electrons, right, we can draw in the products. And then we can label what's most important, which is the base and the conjugate base, because that's what we're going to use to figure out the position of equilibrium. Right? So what do we notice is different about the base and the conjugate base? Well, they look very similar in that they're both the conjugate base of a carboxylic acid. The difference is that this one has 3 fluorine groups that are electronegative, and they're helping to stabilize by withdrawing electron density through induction this negative charge that's shared between these 2 oxygens via resonance. So if this one is more stable because of the electron withdrawing groups, we predict the position of equilibrium will favor the more stable base or the weaker base. So let's go ahead and work on the other ones then. Right, so we have, this will be the base. We'll label that because that's important. Right, and it's going to take one of these hydrogens from the acid. Doesn't matter which one, right? Just draw it taking one of those and then leaving that electron pair behind as a lone pair. Now our first task is going to be to go ahead and draw in the products, I should say. So we have the conjugate acid and the conjugate base. And I'll go ahead and label the conjugate base. That's the 2 structures that we want to compare. So between the 2, we look and see what is the difference, right? The difference is not in the atom, because it's a carbon atom with a negative charge in both cases, but it's that this one has the presence of a nearby electronegative oxygen atom. That's going to help stabilize this lone pair. And that means that this one is going to be more stable, right? And equilibrium always favors the formation of the more stable base, right? So we can go ahead and predict the same position of equilibrium towards the right. And then looking at the next case, right, this will be the base. Let's go ahead and pick up the proton and then leave those electrons behind as a lone pair. We'll go ahead and draw what we formed here. Then you can add in those lone pairs or not. It's a good idea to do it just to be more clear on your structure. Okay, so I've drawn in both the conjugate base, right, and the conjugate acid, and then I'll label the base over here so we make sure focusing on what we're comparing. Right, so what is the difference here? So we have the same atom, right, but this one has an electron withdrawing group that this one doesn't have, right? So if this base is predicted to be more stable due to withdrawing of electron density away from the negative charge towards the nitro group. So if we're predicting this to be more stable, then we want to predict the equilibrium will favor that structure and it will lie to the left. Okay, moving on to resonance effect. Again, that's the R in REO. And that's actually the second most important factor, but we're covering it third, which is okay, I think. And the idea is that resonance structures can better stabilize a base, making it a weaker base. Right? So you get the idea. If you have a lone pair and it's delocalized through resonance, then it's going to be a more stable lone pair, right? That's the idea. And if it's more stable, then it will be a weaker base. So let's go ahead and work on, again, drawing in curved arrows, drawing in the missing products that get formed from the acid-base reaction, and then predicting the position of equilibrium. And looking at the reference, right? Let's go ahead and go over that first. So we have the base taking a proton from the acid, right? Forming the conjugate acid and the conjugate base. The difference between these two is that this lone pair is stabilized through resonance because it's an allylic lone pair, and this one isn't, right? So if this one is stabilized through resonance, we predict it to be more stable, and the equilibrium will favor that more stable compound. Let's go ahead and practice over here. So we have the base, right, taking the proton of the acid. So we can draw in those curved arrows and label the base. And then we'll come over here and we will draw in what we formed. Notice I drew the pi bonds in the ring differently, but remember that those are just resonant structures. You know that the true structure is the hybrid between those, so it doesn't matter which way I've drawn them. Okay, and then we'll go ahead and add in the conjugate base. Right, so comparing the base and the conjugate base, what's the difference, right? So we have the oxygen with the negative charge is the same, but this structure has an allylic lone pair that's stabilized through the ring, through the allylic lone pair pattern. So we know that this is more stable due to the presence of resonance structures that help delocalize the electrons. So if it's more stable, we should draw our equilibrium arrow in that direction. Okay, moving on to the next one. We have the base taking the proton of the acid. Go ahead and draw in what we formed. I just threw in some extra electrons here because I felt like it. So I could visualize all the lone pairs. And then I'm going to label this one as the conjugate base. So again, let's look at the difference between the base and the conjugate base. So the base is not resonance stabilized, whereas the oxygen here on the conjugate base is resonant. One of the lone pairs is allylic and resonance stabilized up to the other oxygen. So in fact, these two oxygens share the negative charge 50-50, right? So delocalization of electrons and charge is more stable than something that's just localized on one atom. So again, more stable, and we predict the equilibrium will favor that more stable conjugate base. Moving on to the next factor, which is hybridization effects. So this tells us that s orbitals can better stabilize a base than a p orbital. And that's because it's spherical and the electrons are held closer to the positively charged nucleus. And if it can better stabilize electrons, right, making it a more stable base, then it's a weaker base, right? And another way of explaining that is to say that s orbitals are more electronegative than p orbitals. Basically, electrons in an s orbital are more stable because they're closer to the nucleus, and therefore you can say that because they're closer to the nucleus, it's just like electronegativity. Okay, so let's use that knowledge to answer question number 10. This one, again, wants us to draw curved arrows to figure out what the products are going to be. Draw those in. Predict the position of equilibrium if it will lie to the left or to the right. And then let's look at the first example that has been done for us as a reference. Right? So this shows us that the carbon here with a lone pair that's also part of an alkene is the base, and it's taking a proton from this other structure. And so this is the acid, right? And then we get the conjugate acid and the conjugate base. The base and the conjugate base are labeled for us. And then notice how it talks about the hybridization of the carbon. So in this case, the carbon is sp2 hybridized, which means the lone pair is in an sp2 hybridized orbital. In this case, the carbon is sp3 hybridized. The same is true, the lone pair is in an sp3 hybridized orbital. Well, an sp2 hybridized orbital has more what we call s character because it's 1/3 s instead of 1/4 s, right? So more s character means it's going to be more stable. The electrons will be closer to the nucleus. And you can think of the carbon as more electronegative, right? And the lone pair simply will be more stable on that carbon. That's why they predicted the equilibrium towards the left here. So let's go ahead and draw in the arrows here. So this must be the base, taking a proton from the acid. Go ahead and label the base. Right? And we'll draw in both the conjugate acid and the conjugate base. Going and labeling the conjugate base is that we're going to compare the base and the conjugate base. So if we're thinking about the lone pair, right, this oxygen is sp3, and this oxygen is sp2. Right? So the lone pair is in an orbital that has more s character, and therefore we should expect it to be more stable, according to Ario, and drawing the equilibrium arrow in that direction. All right, let's go ahead and work on the next one. So again, we have the base taking proton from the acid. Go ahead and draw in what we formed. Right, so we formed the conjugate base and the conjugate acid. We'll go ahead and label this one as the base, right? And then let's look at the difference. So in this case, we have a conjugate base where the carbon is sp3. And in this case, we have a conjugate base where the carbon is sp hybridized. Right? So a lone pair in an sp hybridized orbital is in a 50% s character orbital. That will definitely be more stable than in a 25% s character orbital. And so we're going to again predict the position of equilibrium lies to the right. Okay, so next it puts it all together for you and says, using Ario, we can identify the base and conjugate base, and the equilibrium will favor, and these go in order, right? So the atom is the most important typically, then resonance, then induction, then the orbital. But we'll go ahead and analyze all of these and then come up with a prediction as to the position of equilibrium. Okay, so let's look at the first one, which has been done for us. And it says, we're going to draw the product of the following acid-base reactions. So it looks like it's not going to give us the products. We'll have to go ahead and draw those in like has been done here. And then we're going to predict the position of equilibrium by analyzing Ario. Right? And so what they're showing you here is by analyzing the atom, specifically we're looking at the atom with the negative charge on both the base and the conjugate base. So we're comparing a nitrogen with a negative charge versus an oxygen with a negative charge. And so nitrogen and oxygen are in the same row of the periodic table. Remember, it goes carbon, nitrogen, oxygen, fluorine. Right? So oxygen is more to the right on the periodic table. And that means that we would predict the equilibrium would favor the right. So that's why they've drawn in this arrow going that direction. And then what about resonance, right? Well, if we had drawn in the lone pairs on this oxygen, right, one of them is going to be allylic to the 3 pi bonds that are on the chlorine. So it's going to be resonance stabilized, whereas the lone pair on the nitrogen is not resonance stabilized. So again, resonance stabilization, we predict that will be more stable. So we have the prediction to the right again. What about induction? Right? Well, here we have the presence of an attached chlorine and 3 oxygen atoms, which are all electronegative. This one doesn't have any electronegative atoms attached. Right? So again, we're predicting to the right based on electron withdrawing groups nearby, helping to stabilize that negative charge. And then lastly, we have the orbital. If one of these lone pairs is allylic, then it doesn't count towards the steric number, and this oxygen is sp2. And the nitrogen's lone pairs, right, are not allylic, so both of them count towards the steric number, in addition to the 2 sigma bonds to the hydrogen atoms, and the nitrogen is sp3. So again, an sp2 hybridized orbital is predicted to be more stable with greater s character. So again, a prediction to the right. So this one, all 4 factors reinforce the fact that we should predict to the right. But technically, if there's any disagreement between these, we would analyze in order. So atom being the most important, and only when there's no difference do we move to resonance. There's no difference, we move to induction, and so on. We'll see if we see any of those examples as we move through the activity. Okay, so let's go ahead and think about what's probably going on here. Okay, so unfortunately, this wasn't drawn out super nicely for us in order to be able to draw in the curved arrows. So I'm just going to go ahead and draw it in with the bond from oxygen to hydrogen shown, and then draw in the fluoride atom, because sodium fluoride, right, is a sodium cation and a fluoride anion. This is what we're really dealing with here. And since we see the negative charge, it makes sense to predict that this is the base, taking the proton from acid. So we'll go ahead and draw in the products of what gets formed here. Okay, so we form hydrofluoric acid and this oxyanion. So this one is the conjugate base, right? And so that's what we're going to be comparing here, is this oxygen with a negative charge versus the fluorine with a negative charge. So in comparison here, we have, remember the way it works for the atom is when they're in the same row, right? We say that as we go to the right on the periodic table, the base gets weaker because the lone pair and the negative charge, the extra electron and the negative charge are more stable on an atom that's more electronegative, right? So if this is more stable, then we're going to predict going this direction, right? And then we'll just put in a little note here, say fluorine is more to the left. You could have written oxygen, right, is more to the right on the periodic table. Okay. Did I do that correctly? No, I did not do that correctly, unfortunately. Okay, so let me erase these. So fluorine is more to the right and oxygen is more to the left on the periodic table. Okay, so whatever is more to the right, is more stable. And yes, so more to the right, more stable, but it's actually on the left side of the equation, which is why the arrow is going this way. Sorry, a little confusing myself for a second there. Okay, moving on to resonance. We'll just put a big X and say no resonance on either case. Right, are there any nearby electron withdrawing groups? No. no nearby electron withdrawing groups. And then for the orbital, right, both of those are sp. No difference. Okay. sp3. Okay, so based on that, right, we're going to predict just based on the atom. And remember that this is going to be the stronger base, right? And this will be the weaker base because this is more stable. We're going to predict this direction. Okay, moving on to the next one. We have a phenol, that's what this is called. I am going to just redraw this just so that I can draw in the curved arrows. I just need that bond actually drawn out to be able to properly draw in the arrows. And then this is just hydroxide. I can ignore the sodium ion, which is really just a spectator ion. And then I am going to label the base. Base takes a proton from the acid, and then we'll go ahead and draw in what we formed here. Oops. Sorry. A bit ugly. I'll probably end up redrawing this for the key, just because it's getting a little bit ugly. And then water, the other product. Then we'll label, of course, also we want to know about which one is the conjugate base. Okay, looking at these, right, we have the base and the conjugate base. So we're going to put an X on the atom because they're both oxygen. And then in terms of resonance, though, this lone pair on the oxygen is stabilized through resonance to the ring, right? So we'll say that this one's more stable through resonance, so we'll predict going to the right here, right? We'll say conjugate base, resonance, stabilized. And induction, right? There aren't any nearby electron withdrawing groups. So right, no electron withdrawing groups. In terms of the orbital, right? The orbital on hydroxide, the oxygen is sp3, and then this oxygen is sp2. So again, sp2 is more stable, so we predict this way, right? Versus sp3. Okay, so again, because of these two, they're both going in one direction, so we can predict equilibrium lies to the right. And then over here, we can redraw these as hydroxide. And this one is drawn okay, so I don't need to redraw that one. Go ahead and show the curved arrows, and then draw in the products. The water and the conjugate base. We'll label those. Okay, so we have base, conjugate base. Okay, so this is an oxygen with a negative charge versus a carbon with a negative charge. Right? So we're going to predict that the carbon is less stable with the negative charge. The oxygen is more stable with the negative charge. Sorry. I'm talking and writing at the same time, so I'm not doing a very good job. Okay, we're predicting this is the stronger base, right? This is the weaker base. Based on the atom, we're going to go towards the weaker base, right? And then say oxygen more right. In terms of resonance, there's no resonance. Okay, and then induction, there's no induction. And the orbital, and this would be an sp3 hybridized orbital, and so would this. So again, just write both sp3, no difference. Right, so we're just going to predict this direction due to the atom. Let's look at the last case. We have now we have a positively charged acid, right? We know hydronium ion is an acid. So this will be our base, taking the proton from the acid. Will give us a conjugate acid and water as the conjugate base. So now we're not comparing atoms with a negative charge, however, we're still comparing atoms with a lone pair, right, on the base. So we can still do the same analysis. Right? So what's the difference here? Well, there's no difference, let's say, in the atom, right? Because they're both oxygen. What about resonance? Right? Well, this phenol's oxygen has an allylic lone pair. So there's resonance, which makes it more stable, right? And so we'll say base resonance stabilized. What about induction? No induction. And the orbital, right? There is technically a difference. This oxygen is sp3, right? And this oxygen with an allylic lone pair is sp2. So more stable towards the sp2. Okay. And we're predicting it lies to the left. Okay, so these are all cases when there was either only one factor leading to a prediction or two that are leading into the same direction. But sometimes ARIO doesn't work out quite so perfectly, and we can get predictions in different directions. When you do that, ARIO says you have to look at the atom as being the most important, followed by resonance, followed by induction, followed by orbital. So a prediction to the left would supersede this prediction to the right. So it would be predicted based on ARIO that we should go to the left. But the true equilibrium, right, actually is the opposite. Because if we look at the pKa values, you see that ammonia with a pKa of 35 is the weaker acid. So we would be predicting to go in that direction. We are actually going in this direction towards the weaker acid, but that would be opposite of what we would predict from ARIO. So these are exceptions to ARIO where ARIO doesn't predict the correct answer, in which case we would, the pKa values, if known, will definitely lead to the correct answer above ARIO. Okay, so let's go ahead and see what's going on here with the example before we do the real question here. So we have the base, right? Taking the proton from this acid and then forming the conjugate base and conjugate acid. And then again, these predictions, right, which are based on nitrogen versus carbon with a lone pair and a negative charge. So remember the periodic table goes carbon, nitrogen, oxygen, fluorine. So nitrogen is more to the right on the periodic table. So we would predict that it's more stable going to the left since the nitrogen is on the left over here. Neither one has resonance and there's no electron withdrawing groups nearby. But let's look at the orbital, right? The orbital on the nitrogen is sp3, on the carbon would be sp. So sp actually predicts going in that direction. So in this case, the difference in electronegativity between carbon and nitrogen is pretty small. And the difference in the orbital is larger, going from sp3 to sp. So ARIO would tell us we have to look at the atom first. That's more important than the orbital. And, in 98% of the cases, that will be correct. It's just that it's a pretty small difference in terms of the atom and a larger difference in terms of the orbital. And so it doesn't work out that we predicted it correctly using this way of prediction, which is described in the Klein book. So let's look at another example and see if we can see what's going on here. I'm just going to redraw this as hydroxide. Again, the potassium cation is just a spectator ion. And then I'm going to show base taking the proton from the acid. I'm going to label this as the base. And then we'll draw in conjugate acid, which is water. And then the conjugate base, which is this structure with a carbon ion. Okay, so let's do some analysis of ARIO using the base and the conjugate base. So we have oxygen with a lone pair and a negative charge versus carbon with a lone pair and a negative charge. Right, so we know oxygen is more to the right on the periodic table, and since oxygen is over here, we're drawing our arrow going that direction. And let's look at some more resonance. Right, so this does not have any resonance, but this lone pair is allylic, and it's resonance stabilized up to both oxygens. Right, so the conjugate base is resonance stabilized. We need to point our arrow towards the conjugate base. And then induction. This one does not have any nearby electron withdrawing group, but the oxygens here are nearby to this carbon ion. So the conjugate base has 2 oxygen electron withdrawing groups. Okay, and then let's see orbital. Right, so the oxygen here is sp3, right? And this one, because this lone pair is allylic, doesn't count towards the steric number, right? Then this carbon is sp2. So we would predict going this direction, right? And we'll say the conjugate base oxygen is sp2. Okay, so again, if we were applying ARIO in order, we would say A is more important than R and I and O. We would have to predict that the equilibrium lies to the left, right? This would be, go write it in over here. So ARIO's prediction, in this case would be, in this first case would be to the left here. And ARIO's prediction over here is again to the left, because again we have to apply in order. Right? So let's see if that actually matches our understanding based on pKa value. So pKa value, we know the pKa value is 10, right, for the acid. And then we can compare that to the conjugate acid. And we know water's pKa value is 15.7, right? And so the equilibrium actually lies to the formation of the weaker acid. So this is, right, the equilibrium based on pKa value, which is more accurate than our qualitative analysis of ARIO, right? But it actually doesn't match the prediction. So these are 2 cases where the true position of equilibrium doesn't match ARIO's prediction. So we always have to be careful and know that ARIO is helpful, but it's not foolproof. There can be exceptions, whereas pKa value will always tell us the true position of equilibrium. Okay, hopefully that made sense. Let me know, as always, if you have any questions.